Good afternoon. This is the Colorado uh, Oil and Gas Conservation Colorado Oil and Gas Conservation Commission meeting on October 7th, 2022. We've got an interesting afternoon set up for us here, hearing about different projects that we've funded utilizing the Martinez-Irwin Fund. Unfortunately, Chair Robbins is unable to make it today, so I'm going to chair the meeting today. And I think the first order of business is a roll call. So,
thank you, Mr. Chair. Commissioner Ackerman.
Present.
Commissioner Bogue.
Here.
Commissioner Cross.
Present.
Commissioner McGowan.
Here.
Commissioner Mesner.
here.
Commissioner Oath. Commissioner Robbins. Mr. Chair, you have 5 out of 7 commissioners present.
Thank you, Ms. Larson. With that, we've got 4 different presentations on our docket today. All of these projects have been funded by the Martinez-Irwin Fund to one extent or another. And I think our first presentation is Mr. Duran, who is CEO of Carbon Mapper and research scientist from the University of Arizona. So if we want to bring Mr. Duran into the panel.
Hello.
Good afternoon. How are you?
I'm well. Thank you for having me.
Absolutely. If you just want to start out, and I know that you've got a presentation set up, certainly excited to hear about what you've been doing. But if you could just, for the record, make sure to introduce yourself, the project that you're presenting, and the funding that was provided for that project, that would be helpful.
I'm sure. I'm Riley Duran. I have several hats. I'm Chief Executive Officer for the nonprofit organization Carbon Mapper. I'm also a research scientist at the University of Arizona, which was the recipient of funding for this work. We were funded along with colleagues at Colorado State University, Dan Zimmerly, I think we'll talk later, to do coordinated field campaigns in the Denver-Julesburg Basin last summer and fall to look at high emission methane point sources.
Great. Well, welcome, Mr. Duran, and looking forward to your presentation.
Great. So let me bring up my slides here. Can you guys see them okay?
Yes, we can see them.
Okay, great. So I'm going to talk about multi-scale remote sensing and methane emissions in Colorado. And I'm going to, like I said, I'll focus on the DJ Basin and acknowledge support from our many funders, including NASA, the Irwin Memorial Public Projects Fund, and some philanthropies that support our work across the U.S. Some quick background on the Carbon Mapper program. This is both the name of a nonprofit organization that has a public good mission to make methane and CO2 emissions data available at facility scale globally. And additionally, it's the name of a public-private partnership we've assembled with a number of the partners you see in the upper right to develop a satellite program. And key partners in that include the commercial partner Planet Labs, NASA's Jet Propulsion Laboratory, the state of California, our RMI partners in the NGO space, as well as the University of Arizona and Arizona State University. Program is funded by philanthropy. We're on track to launch our first 2 satellites in fall of 2023. So we're literally about a year out from launching the first satellite. And then we have a long-term goal of expanding that constellation to ultimately provide daily monitoring over most of the methane emitting regions on the planet. And there's 2 ways the data will be delivered. One is all of the methane data will be delivered publicly from Carbon Mapper, the NGO. There's also a rapid leak detection service that our commercial partner Planet will be offering. And as part of this, ongoing airborne remote sensing surveys like the ones I'm going to talk about in the DJ Basin. And so there's more of that to come over the next 2 or 3 years. To give you some framing about where this work comes from and how we applied it in Colorado, is that there is an emerging system of systems of measurement technologies ranging from different satellites in space to aircraft to surface measurements. You're going to hear about various technologies today, and I'm sure in the future. The message I want to leave with you with this slide is that there's no single question people usually ask about methane emissions And so you need a portfolio of methods. And so our research team has been testing this for over a decade, largely funded by NASA, but also NIST and some state agencies. And there are two basic types of monitoring. Type 1, which is more focused on inventory level accounting at the level of states and countries. And type 2 is really focused more on mitigation guidance. How do you get data in the hands of operators and regulators at facility scale so they can act on it? And these things overlap, but as you can imagine, they have different implications on what you need to put in the field. And the other comment here is that, you know, what we're going to talk about today are largely research efforts. They are not yet operational or scaled up, except, you know, I think at a few facilities here and there where people have on-site measurements. So again, just trying to convey the portfolio. The methods that we used last summer in the DJ Basin are twofold. We use both, and I'm gonna give you an example from Pennsylvania where I have some ready animation. So on the left is a figure of methane, it's basically a map of methane emissions in southwestern Pennsylvania. Those are the rusty colors. And this was derived from observations from a satellite called the Sentinel-5 precursor, or TROPOMI. It's a European satellite. And this is a satellite that sees most of a land surface every day, but it's fairly coarse resolution. It's not designed to pinpoint individual production sites. It is to give you regional insight. And so when we analyze this data, we can estimate the net regional emissions from Southwest Pennsylvania, and the number we come up with is about 113,000 kilograms of methane an hour, which is important for giving us context for point sources, which are individual emission sources, and those are indicated in the black circles in this figure. And the way we know those is this animation on the right shows individual methane plumes detected from our other observing system, which is a different aircraft, in this case, either NASA's Avarice-NG aircraft or Arizona State University's Global Airborne Observatory. I'll talk about the technology in a minute, but what you're seeing in this animation is a combination of plumes from coal mines. Those are the very large plumes here, the big ones, and the smaller little purplish plumes you see here and there from oil, mainly gas production. So upstream, midstream activity. And so you're seeing emissions from both coal mining and oil and gas in Pennsylvania. And so when you put these things together, we're able to both estimate the net regional emissions and then these high emission point sources. And then we can infer what else is happening, like area emissions. And in a place like Pennsylvania, that includes emissions from things like farms and agricultural sector, which tend to be more area source in nature. So when we apply these methods more broadly across the US, this is a report we just published in the journal preceding the National Academy of Sciences, where we studied multiple regions. You'll see the DJ Basin highlighted here is one of those regions, where we combine the satellite observations and the aircraft observations to answer a couple of key questions. And one of the questions is, well, what is the contribution of individual methane point sources, individual facilities to the net regional emissions? And what we find across all of these jurisdictions is it varies quite a bit, as you might imagine, but these high emission sources tend to contribute 20 to 60% of the net regional emissions. So that's on the one hand, that's good news, because it means if you can find the highest emitting sources, you can mitigate them more efficiently than trying to fix everything at once. Not to say you shouldn't go after the low emitting sources, but this is a way to get a jump start on it. But there's also a complication, and that is that many of these emissions, particularly in the oil and gas sector, tend to be very variable. And what we find in doing studies over time scales of weeks and months and years is, with repeated observations, is that we tend to see a population of both very persistent emitters, sources that never go away, and those may be more likely to be leaks or malfunctions, as well as highly intermittent emissions, which are more likely to be due to process venting, things that you expect, and or intermittent malfunctions like a faulty compressor seal. So the takeaway from this is that to really get operational understanding of what's happening is we need more frequent sustained sampling. And this is why you'll hear us say that you need a mix of portfolio of measurements, both the satellite and aircraft measurements, as well as continuous monitoring at sites where you can locate on-site measurements. Other quick point, I kind of alluded to it in an earlier slide, is there are two general categories of emissions for methane. There are high emission point sources. Sometimes they're referred to as super emitters in the scientific world, again, because a small fraction of facilities are responsible for a disproportionate amount of the total emissions. it's important to understand the distinction between point sources and area emissions because they manifest differently with different sectors. For example, enteric fermentation from livestock is an area emission spread out over, literally thousands of head of cattle usually, and can be very difficult to measure with almost any method. And that's different than what we tend to see with oil and gas production, coal production, natural gas distribution system, including landfills and wastewater treatment plants, where we tend to see more point source condensed plume activity. And these things have implications on how you use the data. This is, I don't want to overgeneralize, but the tendency with point sources is the approach to mitigation is to locate and minimize the outliers and the malfunctions. Whereas with area emissions, where you're looking at the combination of emissions from a huge, widespread distribution of infrastructure, there are more systemic issues to address. So it's not doing the whack-a-mole thing, finding the malfunction so much. The point here is we need to address both, and I just trying to highlight that our program tends to focus more on the former because that's what remote sensing technology tends to be better at. But just to keep in mind, we need holistically, if we're trying to reduce methane emissions writ large, we need to address both categories at the end of the day. The technology we've been using for finding and quantifying point sources, and this is both true for methane and CO2 emissions, is called imaging spectroscopy. It's a technology that's been under development at NASA for over 3 decades, and it's fairly mature now with prototyping on aircraft and now moving to space. And it can do, relevant to this application, it can do 3 things. And the way imaging spectroscopy works is, imagine you have a camera, but instead of 3 colors, which the human eye is used to seeing, it has nearly 500 channels of information extending into the shortwave infrared. And that means that we can pick out the molecular fingerprints of trace gases like methane and CO2 in the atmosphere. And because it's an imager, we can fly at fairly high altitude over large areas quickly and basically image these individual plumes. And you can see through these examples I'm showing here that it's usually fairly straightforward to see where it's coming from. You can see where the hotter part of the plume is, so to speak, where more of the methane is, or where more of a CO2 is, and you can look at the plume shape to locate where the source is originating. Additionally, because it's a spectrometer, we can retrieve other quantities, and one of them is flare temperatures. So if there is combustion happening, we can detect either the presence or absence of a flare. And this is very useful. It's not so important in the DJ basin, where you don't see as much of this like we do in the Permian and the Bakken. But in places where there's a lot of flaring, you can detect unlit flares by the absence of a flare at a high emission methane source, or you can detect inefficient combustion when you see both the flare signature and a high amount of methane. When you should, if it was high efficiency, you shouldn't see a lot of methane. So here are the results from the summer and fall study from last year. This first slide is addressing the regional question. So what you're seeing here in the red polygon is the study area that we looked at for both the July and September observations. So what you're seeing here is a map of methane emissions derived from the Tropomi satellite using inverse modeling. And each of these simulations was run for about 2 months. So these span the time frame that we were flying the airplanes at lower altitude, looking at point sources. And I'll show you what the net numbers are in a minute. But this is the results we got for September and October during the study period. And then this slide shows in the white rectangles we flew repeatedly. On average, they got about 4 samples over the course of a couple of weeks, in some cases more, over these regions. You'll notice outside of this big polygon, which is focused mostly on oil and gas and CAFOs, that we also hit a few outlier facilities, and some of these are landfills near the domain that we talked with CDPHE about hitting on our way to and from the airport. So we actually looked at big major landfills, both within this domain and outside it. And what you're seeing on the left, the green diamonds indicate methane point sources we detected in just the July campaigns. And then on the right, you see these pink pins that were added in September. And so you'll see a couple of things. One is, in some cases, we see the same source in the same location over the course of both September and July. In other cases, they don't align, right? Which means that they didn't persist over the time scale of 3 months. And this is typical. We see this in most jurisdictions, a combination of, like I said, highly persistent sources and sources that are more intermittent in nature. So if you put together some statistics using the regional observations from the satellites and the net number and the point source observation, you get the following. So for the period, and I'm just sliding around my menu here, for the period July versus September. In July, we detected 92 individual point sources. I should be clear, individual plumes. Many of these, or some of these at least, were repeats at the same site. So it's not to say that we found 92 unique emitters. Found roughly the same number of sources or plumes in September. However, if you add up the emissions from these point sources in summer versus fall, we saw a measurable increase in emissions in going from summer to fall, and that's interesting because we also see a significant increase in the regional emissions. So the column here under point source emissions is just adding up all the individual emitters we resolved with the airplanes. The column on the far right is the regional net emission estimate we got in the summer and the fall. And so you do see a significant, almost 20% increase in the regional emissions and about an 8% increase in point source emissions. So this is giving us some insight into where things are increasing and changing between the summer and the fall. Also interesting is if you look at this by sector, if you look, because we can resolve where these emissions are coming from down at the scale of individual pieces of equipment. In this case, our resolution is about 3 to 4 meters in each image. We can break this out into oil and gas, waste sector, and CAFOs. So these are large livestock operations within the study domain. And if you compare the red circles here for a second, you'll see that the oil and gas emissions increased by almost 70% between the summer and the fall. And so again, this is just the point sources we observed. It's not saying that the net oil and gas emissions went up by that much. It just means that the population above our detection limit increased by about 70%. But if you compare the green circles, you see that it was almost offset by a reduction in emissions from the CAFOs. And that makes a lot of sense because we expect to see higher emission in summer from livestock operations because it's largely manure management. And so in the hotter temperatures in the summer, we expect to see more methane than we do in the fall. And so that makes sense. And it's just noteworthy that this is the kind of variability we're seeing from season to season. And I want to just underscore this because it is still the case that most of the studies we're talking about are highly, field campaigny in nature. That is, you go out, you fly an airplane around for a few days during a month, and then you come back and do it again maybe a few years later. And literally, I can count on one hand the number of studies that have done this over the last 10 years. And so while I would say we don't see a lot of change over the last 10 years in the net emissions from the DJ Basin, we are seeing considerable seasonal variability. And so I think it's important, if we really want to understand what's happening with trends in methane emissions in Colorado, we have to do these measurements more frequently than every few years and not just in a given month, right? The other thing we can do with this data, because we can resolve it to individual sectors and segments, is we can split out the emissions, again, just for the point sources between the summer and fall campaigns at the relative split between production sites and gathering and boosting. And it's right, so one thing that we notice here is a relative reduction in the emissions from production, but we see an increase in, for example, in gathering sources attributed to gathering pipelines. So again, I don't think we're seeing all of the picture, but it shows that there's considerable variability and things can move around by segment, not just by emission sector over time. So these are just some examples of what we saw this is an example from the September campaign where we detected a well unloading, actually pretty close to a commercial business. This persisted over the course of several days, and you can see that actually in this case the emissions are pretty consistent, including minute to minute and over several days. So this is just an example of what we see when we do these flights. This is a relatively large emitter, 1,000 kilograms an hour is on the high side, but it's an example of what we see. Another example I think is really interesting, and I credit our colleagues at COGCC and CSU, in particular Dan Zimmerly, on this example. Illustrates one of the challenges we have with attribution and then a follow-up with these sites. This is an example where we detected over the course of several weeks, repeatedly saw a methane plume near a former production site that had been decommissioned. It turned out it was a gathering line. And so this is the timeline of us reporting it. Then the follow-up observations with people on the ground to try to pinpoint the location. What's interesting, I think, about this, and then the operator took action and excavated and remediated it. I think what's interesting about this example is it highlights the fact that there are potentially multiple first responders, and it's often can be difficult to understand when you first see one of these things, whose infrastructure is it and which agency has jurisdiction also, right? So if you're talking about gathering lines versus, or pipelines versus production sites, and I realize this may not be the case in Colorado, but in other jurisdictions, it is a bit of a challenge. So interesting use case, I think, about if you were to try to scale this up and do it operationally, is how do you get the information in the hands of the right people to do mitigation? So all of the data that we generated last year has been published both in this PNAS paper I mentioned. It's also available on our public data portal. You can see here a map of these are the individual plumes of methane detected in the DJ Basin. You can see some other ones around Colorado, including down here in the San Juan Basin, and additional point sources. Actually, these turn out to be coal mines out to the west. So these are available for download, public viewing. I'll also let you know that we're on track working with CDPHE to do a series of flights like this in the Pisans Basin starting in a couple of weeks. This is an unrelated study. This is actually a research effort funded by Carbon Mapper. And so we are planning to expand this work in the years to come. And I guess I'll close on that with where things are heading next with the satellites. So this is, I mentioned the Carbon Mapper satellite program. Once we start launching satellites next fall, we plan to do periodic global surveys. That's the map, the gold colors here, of where we think most of the methane emitting regions on the planet are, and then sustained monitoring with the purple areas where again, we'll be looking at higher frequency monitoring to assess intermittency and to get data in the hands of operators more quickly. And again, our commercial partner Planet will be offering a leak detection service to operators within a couple of days, about 3 days of each overflight. And then last but not least, with this strategy is us planning to respond to other satellites. There is like as I mentioned, there are other satellites out there that do wider area monitoring. And so we plan to use hotspots that they report to tip, we call it tip and queue in the space business, tip us off to queue our satellites to look at high priority regions. So it will be, a pretty flexible and powerful system. And I think this will complement, I don't think it will totally replace, but it will complement some of the less frequent airborne surveys that we're doing now as a research community. So just to summarize, we actually think that what we're seeing in the DJ Basin in terms of point source emissions is actually a bit less skewed than we see in other basins. It's certainly nothing like the Permian or Marcellus Shale, but it's more than we see in the San Joaquin Valley in California, at least at the moment. So it's not quite middle of the pack, but definitely not in the upper tier. We do see significant regional variability, both in the regional totals and the point source emissions. And we think that a lot of the fall growth that we saw last year was due to both an increase in oil and gas emissions, but offset by reduction in CAFOs. I have to say, I was a little surprised at how high the CAFO emissions were in the summer. We've done a lot of work like that in California, and I think some of the Colorado CAFOs are actually higher emitters than what we see in the San Joaquin Valley in California. So that's maybe it's something for CDPHE to look into further. We don't see year to year, if we go back and look at previously published studies, in particular, Jeff Peischel and Gabby Petrone using mass balance airborne estimates of regional emissions, we don't see I would say, a significant shift in the overall emissions from the basin. But I think you have to put that in the context of what's happened with production rates for oil and gas and development in other sectors, including waste and ag. But we don't see, there's no evidence, I think, of a net shift. I'll just reiterate that we need higher frequency monitoring if we're really going to constrain this variability. And that is not unique to Colorado. It's true in every jurisdiction. We're going to do the overflights out west in a couple of weeks. And like I said, look ahead to more frequent satellite observations and sustained observations starting about a year. And the last point is back to my example with the gathering line. I think as you see more methane data like this coming online, particularly third parties like Carbon Mapper and other NGOs and even communities, I think there's going to be need for more developing avenues for more expedited notification of operators. In other words, if the data is coming from outside the fence, it isn't something that the operator is funding. I think it makes sense to establish some mechanism for notification. I think we're all trying to avoid something like the 1-800 smoking car approach to notification. And so, but maybe that's something for Colorado to think about as you see more of these data sets coming online. So with that, I'm happy to take any questions.
Wow, that was a lot of information. Thank you very much. Appreciate that. Commissioners, do you have questions?
Chair, if I might.
Sure, go ahead. Sorry. I'm
Thanks.
not used to seeing the little hand. I missed it.
No problem. Thanks so much for the presentation. That was wonderful. You probably said this at the top, so apologies, I didn't write it down, but can you remind me the cost of one of these field campaigns for an individual flight sequence over a domain for a given month?
Yeah, these tend to be quantized because it's not efficient to go out and do like a couple of days because you have to stage the airplane. We're doing these flights all over the north, basically Canada and the US. I can't remember off the top of my head. I think the total cost for this project was on the order of about 800K for both the combined summer and fall campaigns, including the airborne observations, largely dominated by, frankly, fuel cost with the airplane. In our case, we use fairly high altitude aircraft. These are not aircraft flying over an individual field. You saw the size of the DJ basin. With the aircraft we were using in this campaign, the Global Airborne Observatory, we were doing a complete survey in about 2 days. And we did multiple surveys over the 2-week period, and then we repeated that in the fall. So, and when we're using NASA aircraft, we can be operating as high as 28,000 up to 45,000 feet. So we're not, these are not Cessnas; these are big airplanes. So yeah, I think that number, the total project cost was in the range of 800K, but I can get back to you on the final number. Other thing I'll mention is that, and I think this is probably true with some of the other researchers, is there are significant in-kind contributions. Like these programs, because they tend to be researchy, they're building off of multiple agency programs. And in my own case, we benefit significantly from in-kind funding from NASA under their multi-scale research program. And then, as I mentioned, with the upcoming flights and the Peons, we're actually, as an NGO, we're funding those flights ourselves. So I think you're seeing a mix of funding from this particular fund in Colorado, as well as federal and philanthropic contribution.
Thank you.
Other questions from commissioners? Commissioner McGowan?
Thank you, Mr. Chair. And thanks for the summary of your project. It's helpful to have someone talk about it, present it, and see it visually. I think if I'm understanding what you're saying is that someone did a flyover, maybe multiple flyovers over the past 10 years, and that even though the oil and gas industry has been growing, emissions have stayed about the same?
Yeah, I think I suspect that Alan Freed, who I think was going to speak next, maybe we'll say more about this, because they used, I think, more of an apples and apples comparison. So the way the studies have been done in the past in the DJ Basin is someone goes out with a research aircraft, they fly a perimeter around the area, think of it flying a big box, and they can estimate a total number. What the advantage of that technology, those technologies, is they are in situ samplers. They're actually sniffing the air with analyzers, and they're measuring more than just methane. And so those previous studies I mentioned, because they can measure other alkanes or other tracers, they can actually do source apportionment. They can say how much of this is due to oil and thermogenic versus biogenic sources. And so I think I'm going to defer to Alan to see what he says about potential trends in the oil and gas component. But I'll just reiterate, yeah, we don't see our satellite-based estimates, which are just looking at methane, don't see a net change. It's neither going up nor going down. And so then, yeah, then the interesting question you've raised is, well, why and what was changing, and how much of that was due to it actually a net reduction in intensity, for example, if production was increasing. So I guess I'll defer to Alan to see what he and Russ might have to say about that.
Okay, thank you. And then I wonder, and maybe this was in the presentation and I missed it. When you saw super emitting instances, did you find that it there was something repetitive that was, so, you know, the example that you gave was liquids unloading, which I'm not sure that we've really explored as a state yet, but I'm wondering if there was some sort of something that popped up frequently where we would be able to go back to operators and say, you know, in this flyover, we saw X number of times this kind of activity was leaking. So everybody needs to go assess, check, double check to make sure that this type of equipment is not leaking.
Yeah, I think, yeah, I understand. Where we've done a lot more overflights in places like the Permian Basin, like, you know, dozens of looks over the course of a few years. I'll just say that we see two general things. We see that about half of these high emission sources tend to be persistent. They're there at least half the time. In many cases, they're there month to month, year to year. And those when we have followed up with operators, they tend to be malfunctions. The other 50% of these high emission sources, I mean, I'm using general trends, not just Colorado, but across the US, tend to be much more intermittent. And sometimes they're only active 5–10% of the time. And that's more complicated to diagnose because a lot of those are probably, in fact, we have confirmed are planned process emissions like periodic venting that are perfect, you know, they're all permitted, they're captured in the reporting program. But sometimes we also see intermittent malfunctions. And I'm thinking here of things we sometimes see at compressor stations where a given piece of equipment acts up at some cadence, and it's periodic, but it's not predicted. I think Dan Zimmerly is going to talk later, and I know he in particular has been looking at this question of how to connect what's expected versus what we're seeing with the airplanes. And I think, unfortunately, I can't stay around for his presentation. I want to see what he's found, but I think he's probably better positioned to address that question.
Thank you so much for sharing today.
My pleasure. Thanks for your time and interest and support.
Are there other questions from commissioners? I've got just a couple of questions. So I think one of the things that stood out for me was the indication that 20 to 60% of emissions, point source emissions, were coming from less than 1% of the infrastructure. And so, I mean, that seems like a really big number, but also potentially a solvable number because it is an infrastructure related item. Is that kind of one of the big conclusions that comes out of these? Yeah,
and just to be clear, for the DJ Basin, it's closer to 20%. It's on the low end, but speaking across the U.S. writ large, the 20 to on average about 40%. We found that in California with our initial survey starting back in 2016, and so we call this the low-hanging fruit argument, or it's not even low-hanging fruit; it's fruit laying on the ground if you know where to pick it up. And I think that's the challenge here is that some of these are fairly large areas. I know Dan and others would argue this shouldn't be stochastic, but at the moment it is because we don't understand the system as well as we should. And so because we don't know in advance where these things happen, this is why I think there's a priority to go find them, because absolutely, if you can pinpoint high emission sources and if they turn out after follow-up, investigation by the operators to be a malfunction or a wasteful process emission, then yeah, you can absolutely do something about it most of the time. The last thing I'll say on this point is we've been gathering statistics and sharing data with operators in places like California, Colorado, New Mexico, Texas, Pennsylvania, and the data is still coming in, but at least in California and maybe early signs in the Permian, about 50% of what we're finding above our detection limit, operators report back and will say it's fixable. meaning it's either a malfunction and should be covered under an LDAR program, or it is maybe not unexpected, but it's higher than they'd like, and they think they can do something to reduce the waste. So yeah, I think there's optimism that there's a lot of room for voluntary action if you can get data into the hands of the right people at the right time.
That's great. I think my other question is, you had utilized one category as you were looking at both point source emissions and I think net emissions, which was production. And I guess I was trying to understand like the definition of production. Does that production definition include pre-production or any construction activities prior to kind of general production? Or is that a separate category that perhaps wasn't captured in these flyovers?
Yeah, that's a good question. You know, to be completely honest, we don't know in this study because we weren't resourced to go engage with operators and get asset level activity information. When I said we attribute it to production, it's a spatial indication. We have high resolution camera on the airplane with about 70 centimeter resolution. So when we see a methane plume, we look at the camera image and we go, it's coming from a well pad, versus it's coming from a gathering and boosting piece of infrastructure, or it looks like it might be a gathering line. So we are literally, in this case, we've done other studies in other regions where we have more robust asset level data, but in this case, we're just purely making a judgment call based on an image. We don't have any information about where they are in the exploration or production.
Okay, thanks for that. I don't have any other questions right now. I really appreciate the information. Certainly, I'm going to review the slides and try to absorb it a little better, but that was super interesting. So thank you for being here with us today.
My pleasure. And feel free to, I think you guys have my email. Feel free to follow up if there are any additional questions.
Great. Thank you. So I think next up we have Mr. Freed and Mr. Dickerson from the University of Colorado and the University of Maryland. I did want to just, I probably should have said this at the beginning, but I think one of the reasons that we're getting these presentations is both to learn about some of the projects that have been funded, some of the progress that's occurred over some amount of time, and or any conclusions that have come from the particular research that has been associated with funding from the Martinez-Irwin Fund, but also to create a baseline level of education and understanding for all the commissioners. We've got some commissioners at different levels of expertise or timelines associated with being with the commission. And so are trying to get everyone understanding what we funded, what's been going on as we look at perhaps funding additional projects in the future. So thank you both for being here this afternoon and sharing with us your project. Oh, looks like we need to promote Hannah Daly to the panel.
Yep.
Yeah, she's a graduate student. Those are the people who do all the actual work.
Right. So let me, can you see my screen? If, let's see.
Not yet.
Okay. Can you see that now?
We cannot see it yet, no.
Okay, do I need to get permission to show the screen? Let's see, oh, here it is, share screen. Okay, here we go. How's that? Can you see that?
Okay, we can see your screen, yes. It's not in presentation mode, but we can see it pretty well.
Okay, is that any better?
I think that's in presentation mode, but we can see two slides at once.
Switch screens. You've switched presentations. This is the one you should be seeing, Alan.
Okay, okay.
Swap display. That's it. Yeah.
Okay.
Bingo.
That looks good.
Okay, very good. So this is going to be a tag team effort. My name is Alan Freed. I'm a senior research professor at the University of Colorado, and Professor Russell Dickerson, the University of Maryland, and Hannah Daly is a graduate student of Russ at the University of Maryland. So we'll tag team together. And then there are many other people, as indicated here, from both the University of Maryland, as well as my group at the University of Colorado, and Abby Koss at TopWorks in Boulder, as well as Alan Brewer at NOAA, all provided extremely important information. By way of an overview, I want to give you the end result, because Riley gave a very, very nice presentation, and the end result is we're seeing almost exactly the same thing in the fall of 2021 for methane emissions over the DJ. Almost the same number, and by inference, essentially no change from some of the earlier studies. And I'll go into exactly how we arrive at that conclusion. So we're going to be presenting methane and ethane and volatile organic compound, carbon compound fluxes in Colorado over, and there's a mistake, this should be the Denver-Julesburg Basin in the fall, okay? And you can see my cursor, can't you, as it's moving around?
Yes.
Okay, so this by way of an overview, and really doesn't require any overview. The DJ Basin is a large oil and shale basin extending from southern Colorado up into Wyoming and into Nebraska. And our studies were funded as a result of a dramatic explosion that happened in 2017 when a methane line, when a line was inadvertently cut and caused an explosion. And this was the follow-up lawsuit was the genesis of funding our study. One of the ironies is that there's methane sources and methane leaks from a variety of causes. And despite the fact that we have millions of dollars worth of equipment on the University of Maryland aircraft, here's an example of a leak right outside the hangar of our aircraft, where every time we walk by the hangar, we would smell smells of mercaptans, which are indicative of natural gas leaking. And we reported this, and we kept saying, they kept telling us that there was no problem. So Russ Dickerson had the great idea, let's spray this with a soap bubble solution. And here you can see an excellent example of a methane leak occurring locally from very simple method of detection. And they soon fixed that leak. With that picture in mind, the public service came out and immediately repaired this leak. By way of an overview, this is the Denver-Julesburg Basin that we're flying over. So what I show here are the flights from Gabby Petrone in 2012, given by the black perimeter, and the red perimeter is flight tracks of the University of Arizona flights that you just heard about. And over the DJ Basin, there are a significant number of methane sources, including all these little gray dots, which are indicated of oil and gas operations. And there's something on the order of about 48,000 wells, about half of which are active in 2021. There are also other sources, as Riley pointed out, and those are from dairies, from feedlots, from a whole host of other sources. And so you see those sources outlined in our study area. And over Weld County and over the DJ, there are two main sources, as Riley pointed out, of methane. Those from CAFOs, concentrated animal feedlot operations, and also from natural gas or fracking sites. And one of the advantages we have in our study is that we can discern differences of the sources between the animal operations and natural gas by looking at methane-ethane ratios. So methane is emitted from a whole host of sources, as we indicated, but only ethane is co-emitted with methane from oil and natural gas sites. And as you'll see a little bit later on, by looking at the correlations between ethane and methane, you can get some idea of the source apportionment. And just by way of overview, here are the results from previous studies, the Patron study in terms of methane emissions. And these are in units of metric tons per hour, or 10 to the 6 grams per hour. So you can see the values of methane, and we'll be comparing our results with these results. And then they did a source apportionment by a number of techniques, which I won't get into, and they were able to attribute about 70% of that due to oil and natural gas. And Peichel's study in 2015 also measured ethane emissions. And I call your attention to this number, because this number you're going to see from our studies has gone down by a factor of 3. So just to keep you apprised of what's to come. So this is the study area, and the thrusts of our study, the goals, is essentially to identify any local hotspots to derive emission fluxes based on a mass balance approach, and I'll talk about that in a moment, and to see if the emissions are growing and maybe what impacts these emissions might have on the air quality throughout the Front Range. And Hannah will get into this a little bit more in depth, but essentially the University of Maryland's instruments mounted on the University of Maryland Research Foundation Cessna aircraft is shown here on the left, and our high precision, high accuracy ethane instrument is shown here on the right. And there are a lot of challenges in mounting all these instruments on such a small aircraft. And that is to literally, how do you physically fit these complex spectrometers in such a small space? And then the second issue is one of heat management. As you can imagine, in the fall, and with all the instruments operating, we sometimes got up to cabin temperatures over 100 degrees Fahrenheit. So it was quite a challenge to keep things operating in such an environment. So here we show the inlet of all these instruments. We draw air in through an inlet port mounted in the nose cone of the aircraft. And again, Hannah will talk more about this in a few slides later. So we conducted a number of flights over the DJ, and here you see all the flights. And I'll focus in particular on 2 flights today, the 1st of October and the 5th of October of last year. And what I indicated here are mass balance flights. And what I mean by a mass balance flight, and Riley very nicely gave a preview of what we mean, is we define a box about our region of interest. In this case, this is the DJ basin, and we simply look for outflow plumes, elevated plumes of whatever gas we're looking at, and we look for the corresponding inflow plumes. By taking the difference between the concentrations in the outflow minus the inflow, we can derive a flux. It's a little more complicated than that, in that we have to do a number of assumptions. That is, we integrate the plume across the width of the plume, and we integrate from the surface up to the top of the boundary layer. And there are a number of challenges associated with this approach, and that is, you need to accurately assess that the outflow region is accurately reflected by the inflow region. That is, you're not seeing any additional sources of information in the outflow that does not flow through the inflow. And we get this by what's termed trajectory analysis. And so what a trajectory analysis is, it's a meteorological calculation that looks at the winds from the outflow and the inflow regions. And from the visualization of these winds, you can back out information about how representative the inflow and the outflow are related. The second challenge is that, as you can imagine, is that we're integrating across these plumes. So you need to be certain that the winds have not changed. So for example, if you start out with a very slow wind speeds at the inflow, you can derive errors in your fluxes because the measured flux at the outflow might be significantly different. So we use a technique called a mobile LiDAR system, and I'll talk about that in a moment. So here is and I'll walk you through this. So what we show here is a flight track on the 5th of October. And this is on using the Cessna aircraft. And we color this by methane. So you can see local hotspots of methane over the DJ. And we see this persistent set of plumes over the Greeley Weld County Airport. And this is due to concentrations of oil and gas and CAFOS activities. And we see this very persistently. So what we also show is a plume that we've identified as an outflow region. And this arrow, black arrow, shows a typical wind direction. And what we also show are these black dots. These represent back trajectories. That is, we can calculate where the air came from in 1 hourly basis. And we show from these back trajectories that the air came from this region here, which we designate as our inflow region. We also use forward trajectories, which are given by these red circles, which predict where the air is going to. And the importance of using both back trajectories and forward trajectories is that it gives us a strong indication of the inflow region. So for example, if we were to use this leg here as our inflow region, we would have errors in our calculations, because I don't show it, but these inflows go way off the map. So essentially, using calculated trajectories, we can get very good information about how coherently related the outflow region is to our inflow region. Okay, and so I mentioned before, we use what's called a mobile LiDAR. A mobile LiDAR is nothing more than a laser-based system mounted on a truck. And so this is Alan Brewer's group at the NOAA Aeronomy Lab in Boulder, Colorado. And what they do is they project a series of laser beams, pulse laser beams, up to the upper atmosphere. And these beams scatter back because of dust particles in the atmosphere. And they collect the scattered light, and that scattered light contains a lot of information about the wind speed and wind direction. And since this is moving, we get a mobile picture of the winds, and you can time the information by looking at the pulse return time. So you get a time dependent and a spatial dependent information about the winds. And so here's an example. So the mobile LiDAR was traveling along Route 34. This is again the October 5th flight, and it traveled through Greeley and then down to Wiggins. And so this region, which is not quite perfect aligned with our outflow region, but it's near enough, gives us information vertically, spatially, and time-dependent information about what the winds are doing. And we can compare those with our measured winds. So our measured winds are only at one specific altitude, whereas the LiDAR, the mobile LiDAR, gives us an integration of the winds information over the entire depth of the boundary layer. And that's very important. And likewise, the inflow leg from the LiDAR gives us information very close to our measured inflow region. So this is something that's very unique to these measurements. Other measurements really don't have, or publications about mass balance results don't have this really important supporting information. And I can't overemphasize the importance of this in our analysis. So just to give you an example of how important this is in our analysis. So this is the average winds, average from the surface up to the top of the mixed layer, and average over the entire basin. And we can compare those average winds with our measured winds from the aircraft at a specific altitude. And again, this is specific altitude, but this is the information that we're really after. And you can see the average winds over the entire basin and over the entire altitude range agrees with our snapshot measurements at a specific altitude to within 10%. And likewise, the wind directions are also fairly consistent. So this is the outflow region. And then in the inflow region, something very similar. And from the LiDAR data, we can derive a correction factor because what's happening on this particular day, the winds start out slow in the inflow, and they start to speed up later in the afternoon when we're looking at our outflow sample. So this is giving us a correction factor to the wind velocity measurements, which are quite important in deducing our flux. So Hannah will now take over for the next several slides to show some results.
Okay, thanks, Alan. Yes, my name is Hannah Daly. I'm a graduate student at the University of Maryland, and Phil Stratton and I had the opportunity to be an onboard research scientist during the flights for this field campaign. Next slide, Alan. During this campaign, as Alan said, we really optimized the loading capacity of our Cessna 402B aircraft, and we were able to capture a rich data set. So as Alan said previously, Colorado installed their CAMS-3 ethane instrument, which is on the port side of the aircraft, or the right side of the bottom lower left image. The University of Maryland supplied our ozone detector, as well as a Picara, which measured carbon dioxide, carbon monoxide, and methane, and that was installed in the starboard rack. We also deployed a variety of instruments to monitor GPS position and meteorological variables. And how essentially these instruments work is on the picture to the right, there's a red box that's looking at the tip of the nose cone where we have an inlet, which is pulling with a series of pumps. We pull in air, essentially sniffing the air that we're flying through. And also on the top of the nose cone, we have meteorological sensors, which is on the bottom right image that you can see a little bit better. And that's able to give us an idea of the relative humidity and temperature and pressure that we are sampling. Additionally, ToughWorks installed their ELF proton transfer mass spectrometer, also known as a Vocus ELF, and that allows for instantaneous monitoring of volatile organic compounds. And as was mentioned, I believe it was by Riley, this is a very important instrument to have on board because we were able to further detect the sources of our methane and ethane, such as teasing apart CAFOs and oil and gas and other signatures better. So here you can see the Vocus ELF, and that's, oh, sorry, can you go back? It's a little bit of a tight squeeze getting it on board, but just barely fit through the door, and you can see it as we enter the aircraft there. Okay, next slide, Alan. So now I want to address two of the challenges that Alan touched bases on. The first was establishing or calculating an accurate boundary layer depth, and also determining a proper inflow and outflow region. So it's very important to determine an accurate boundary layer height, because as Alan was saying, when we are doing the mass balance calculations, we are multiplying our difference in concentration by the plume length, as well as the boundary layer height. So it's very important to have this accurate for our flight. So when we are determining the boundary layer, we do this by capturing a vertical profile of the atmosphere, either by doing a spiral over one point or by doing an en route ascent. So looking a little closer at this one flight on October 1st, the tracks are shown on the figure to the right, and the colored line represents methane concentration along the track. The yellow arrows indicate the relative wind speed as well as wind direction. And for this flight, we took off from our home base airport. It's in the kind of on the left side, and that is the Rocky Mountain Airport. We proceeded to go northeasterly, capturing our inflow, or what is upwind of our target region. We took a pretty hard turn towards the west. We did a low approach at Greeley, which is again an important area that Alan mentioned, always sampling high methane due to its proximity to a lot of CAFOs and oil and gas operations. Here for this flight, we did a partial spiral up, and then we continued an en route ascent. And for the rest of the flight, we did 3 different track altitudes of our outflow region, which is in the red box, and we circled around back to our home. So on the plot to the left, we are looking at the vertical profile of the atmosphere, which we did using an en route ascent for the majority. And from left to right, we have methane, CO2, water mixing ratio, potential temperature, and wind direction. So the information we're getting from this is, first off, the top of the boundary layer height for this flight looks to be just above 1,300 meters above ground level. And we can tell this by looking at where our greenhouse gases and water is doing a sharp drop off. And that's also where you're going to see a slight and gradual increase in your potential temperature. In addition to getting this valuable information for the accurate boundary layer height, this profile can tell us about the how well the boundary layer is mixed. And also for this case, looking at methane, we can see, although there is some variability in methane with height, overall it does remain high throughout the boundary layer, and even with some of the highest concentrations being towards the top of the boundary layer. Okay, we can go to the next slide. So continuing with this flight day, I want to address the other area of concern here, which is trying to identify proper inflow and outflow regions. Alan did an excellent job talking about high split trajectories and also using and capitalizing on the mobile LiDAR data. So I don't want to double dip on that. But for this flight on the October 1st, we had a little bit of a different approach, and that was looking at different regions for inflow. So when we're trying to determine our background, we can either do use the inflow region, which is denoted by this black solid box that Alan's pointing to, or we can capture the edge of the plume, which is the dashed black box that Alan is pointing to, or the yellow box. And the edge of the plume is capturing what's just outside the plume region and the target region. So both of these are valid ways for determining a background for a mass balance calculation. It just depends on what's best for each flight. And then for this flight, we opted to take the average of both background C, which is the yellow edge plume, as well as background A to determine our overall background concentration. And for other flights, we sometimes just use inflow, or we can further look to see what's best for each flight. And next slide. So here's a quick look at the high split back trajectories that Alan was talking about. This is one that Phil performed. So every 45 seconds on the outflow legs, so at each of the altitudes, we calculated this 6-hour high split back trajectory, which is just to confirm indeed that the air that we're sampling in our outflow region is indeed coming over our target area. And we continue to do, not shown, but we also do the forward trajectories that Alan was talking about to make sure our inflow region is passing through to our outflow as well. Next slide. Lastly, I do want to mention that our analysis is complemented and seems to go well with Riley and Dan's analysis using downward looking column methane. I'm not sure if think they might be talking either later today or this month. So we'll excited to hear more from their work. And now we can pass it off to Russ.
All right, actually, I'm gonna just briefly.
Sorry, Alan.
Yeah, no problem. I'm just gonna summarize our results. So again, the earlier studies by Petrone and Peischel for methane are given here. And the source that was apportioned to just oil and gas given here, again, showing in the fall that about 70% of the total methane from the basin is attributable to oil and gas. And then our results are shown here. So we had 2 flight days, a little bit different from one another, but the average is in remarkable agreement with the University of Arizona results that we just heard about. And we do what's called a crude source apportionment, where we can determine how much of this methane is attributable to oil and gas, and I'll show that in a second. Okay, so just to summarize, before I show that correlation, we're getting a total methane flux almost precisely on what Riley just showed from his high-flying aircraft using a slightly different approach, which is really remarkable to have 2 independent techniques really complement each other. But I stress that we need to look at additional days to really confirm this, but this is in really remarkable agreement. And this is despite the fact that there's about a factor of 2 increase in the production between 2015 and 2021 in terms of oil and natural gas production. We're seeing essentially no change in the methane flux over the DJ with earlier studies. However, What's very interesting is we're seeing about a factor 3 decrease in the ethane flux compared to Peichel's value in 2015. And maybe if Dan Zimmerly has a chance, he can talk about what we think might be going on here. But this shows that there is a significant decrease, and we have a lot of confidence in these numbers. And then we're getting, and I'll show in a second, from a crude way of doing a source apportionment, that about between 73 and 83% of the methane is from oil and gas production during the fall. And the way we get that is, I don't want to get too far into the weeds, but we define this inflow or influence region. And we do that by using the trajectory analysis again. And what we do is we plot the methane concentrations in the inflow region versus the ethane concentrations. And by looking at how well they are correlated, that is the correlation coefficient, you can get information that in essence says, in a crude way, how much of the methane is correlated with ethane, which comes from oil and gas. The CAFOS does not have these correlations as shown here. You get very high methane without the corresponding increase in ethane. So we're getting a number in this particular case from this flight of about 73%, which is actually in remarkable agreement with some of the other results that have been presented. And now Russ is going to take over and take us to the end.
Okay, I'll make this quick. One of the interesting questions you might ask is, how do these direct measurements of methane flux compare to inventories? And the way we can do that is with a numerical model. So I'm going to show some very preliminary results in which we used a numerical model, next please, called a chemical transport model that models the whole US and is focused down on Colorado. Now, these are just preliminary results, so you won't see too much yet. So you get down to about 1 kilometer resolution when you're right over Colorado. That's pretty good. And what we can do is take one of the official inventories. What we're using is called EDGAR for the Emission Database for Global Atmospheric Research, put together by the Europeans, and see if the numbers that come out of the model look like what we measured. Now, spoiler alert, they don't. The official inventories are way low for Colorado, but they're way low for the Marcellus and for Baltimore, Washington, New York, and Boston too. So no real surprise there. So there's some details here that on how the model was run that you probably don't need. Next, please. And this is a little animation to show that if you put the emissions into the model, it can forecast. The hotter the color, the higher the methane concentration that's forecast. So you can see where you would expect to find a plume, just some pretty pictures. But how well are we doing? Next, please. And we call these snake and curtain plots. The curtain background is what the model puts out, and the snake on top is the actual flight track. That's where the airplane was. And again, the hotter the color, the higher the methane concentration. And for sanity, the models can do everything. And they also do carbon monoxide, which doesn't come so much from oil and gas operations unless there's flaring, but it comes from cars and trucks, also biomass burning. And you can see in general that the model has green where the observations are showing red, so that means it's low. In the lower left, we have a scatter plot where the x-axis is what was observed from the Cessna, the y-axis what the model predicts, and you can see nearly all of the points the model is underestimating how much methane is there. But the same is true for carbon monoxide. That's a useful quantity because you can ratio those. So the question is, what do we do now? We know that the emissions inventory is low. We've got more work to do to make sure we're getting the weather simulated right. And then one of the things we can do is tweak that emissions inventory or use other emissions inventory. Thanks. Yeah, 7 is much less than 25. We can tweak up Edgar, or try different emissions inventory until the model begins to look more like the observations. And that will help us knowing how much and where the emissions are coming from. Next, please. I think that's, and one of the other tricks we can do is ratioing to other trace gases that, that we know about, like CO and CO2. Hannah, do you want to talk about that? Or have you muted yourself?
Sorry, I did mute myself. Yeah, essentially, what we were doing was determining the CO flux for the same region that we used for methane. We did this for methane, CO, and CO2 to look at the ratios. So for the CO flux on October 1st, that was approximately 8.5 tons, and the ratio is approximately 2 in terms of methane over CO, which is, I believe that's about double what we are typically seeing in the regions on the Northeast that what we're used to.
More like 4 times. Well, no, double, you're right. So, but not unsurprising for oil and gas operations. It shouldn't look like Baltimore.
Right.
Or Denver. Keep going, sorry. So
Next one, what do you want?
did we lose you? Okay, this is just some details on how the fancy device for measuring hydrocarbons, the proton transfer mass spectrometer, works. We're running a little late, I think. So let's keep going. So here's an example. And why are we doing this? Well, along with methane, the oil and gas operations can emit more reactive species, and Denver and sometimes the whole Front Range have a problem with photochemical smog and with aerosols that can impact the environment and human health. And so this is just an example plot. C8 aromatics, that means things like xylanes. These are solvents. They're also co-emitted from oil and gas operations. And you can see that they're correlated with methane there. So if they're correlated and we know how much methane is coming out, we can estimate how much xylane in this case, or other toxic or smog producing species are being emitted into the atmosphere from these operations. And I think that's of interest to the people who worry about air quality in Colorado, as well as climate. Oh, and let me just point out that I'm very impressed with how the progress Colorado is making. I'm a member of the Maryland Climate Change Commission. I'm a commissioner of our Climate Change Commission. And so we're trying to figure out where our methane comes from too. This is a big table. You don't need the details. It just shows you some of the species that can be measured. And some of them, like this one with the CN on it, that comes from forest fires. And because the correlation was weak, that's a small number, 1 is perfect, methane has to be perfectly correlated with itself. It says for the days we were flying, there were no sign that any of this methane was coming from forest fires. So on other days, we will see it. Now, there are other species like ketones, that's acetone there, the 0.88, go up a little bit, there we go. And acetone is important precursor to photochemical smog. It's also fingernail polish remover, but we don't think that's where it came from. Other species that are biogenic. Now, benzene is particularly toxic, but there's some good news here for you. In some of the previous studies, benzene was measured in high concentrations, but it was so low when on this particular day anyway that we couldn't measure. It was below the detection limit. Some of the other species like toluene and these xylanes and trimethylbenzene, they were measurable though. So let's keep going. There's a complete diagram here. There's more than you can digest, but you can keep these numbers to tell you which species are likely related to oil and gas operations. They're highlighted, and the ones that are not are just in plain colors. So we do have some contribution from oil and gas operations to aerosols and smog, photochemical ozone, but not benzene on these particular flights. So that's a good thing. Next, please. Okay, these are just maps of acetaldehyde. That's a precursor to photochemical smog and PAN. PAN is what burns your eyes in Los Angeles. It's an important contributor to photochemical smog. And here's some isoprene. These are pretty low numbers because the Front Range is not noted for its heavy broadleaf forests. We would see 10 times this much in the eastern US. So that's just an indication of how much natural biogenic hydrocarbon we're getting. It's very measurable, but it's a small concentration. You mix that with car exhaust, you get smog. Okay, very quickly, this is that's methane versus acetaldehyde. So you can see they're in lockstep there. So we think we know. We can quantify how much acetaldehyde is coming out. Let's keep going. And toluene looks pretty good. That's also positively correlated. But benzene, nope, we see nothing, basically, just a shotgun spatter. So and the concentrations are quite low. So that's good news for air quality in Colorado. And here we go. I will let Hannah, who's actually had her body in the airplane most of the time, I'm too old to do that anymore, give us conclusions and say where we're going from here.
Okay, great. So in general, the main result is that we're seeing no change from 2012 to 2015, despite a factor of approximately 2 increase in natural gas production. And we just analyzed the 2 flights that are good for mass balance. We do have one potential additional one and more flights to process moving forward. We're using Lagrangian and Eulerian modeling, which is being started and shows promise. In terms of photochemical smog, I think the use of our VOC detector will help with understanding improving that. And in terms of methane, we're looking at a total flux of about 25 tons per hour in 2021. And our results do agree with the University of Arizona's results. And again, they show no change from 2012 to 2015. In terms of ethane, we're looking at a flux of about 2 tons per hour, and there has been an improvement from the 2015 Pyschel value of 7 tons per hour. As preliminary analysis, we're looking and regression correlation analysis, we're looking at a 73 to 83% of methane in the DJ Basin being associated with oil and gas operations. That are our conclusions for today. I think this is our last slide, right, Alan?
Yep.
Okay, great. Thank you so much. And we can open up the floor for questions.
That's great. Thank you all for the presentation. I feel both a lot smarter and perhaps a lot dumber at the same time. So
We apologize for getting into the weeds, but I thought it was important to show everything that goes into the analysis.
absolutely. No, I really appreciate that. I'm just making a joke, but
I know.
commissioners, are there questions for the presenters? Commissioner Cross.
Thank you, Mr. Chair. And I just have a couple kind of baseline questions. I just want to make sure I'm understanding some of these conclusions. The no changes with respect to methane, correct?
Yes.
There was a decrease in ethane.
Yes.
Okay. And then can you tell me again, what was the difference in elevation or altitude of the flights between yours and the Arizona one?
So the Arizona was flying, if I understand, somewhere around 26,000 feet, looking down, and we were flying several hundred feet above the surface in our inflow region. And
If I may, let me, there's something even more fundamental than that. What Riley was doing, and it's a very good technique. It's expensive compared to ours, a little more economical, but it works very well. They look down and they give you everything under the airplane from the sunlight that's reflected off the surface, and they can then back calculate the emissions. We actually suck air into the airplane and measure it, and then look at how much wind we have, multiply those two together and get the flux. And in this case, they agreed really very nicely. Though we could only use 2 flights to do a direct calculation, which, as you saw Alan, who used to work for the National Bureau of Standards, fussing his way through the precision of better than 10%. But we've got another at least half a dozen flights, and they're useful for model comparison. So we will get a lot more data. So yeah, the altitude of that downward looking device is not terribly important because they're calculating the flux with a different technique. They measure how much there is total in the atmosphere under the airplane, whereas we measure the concentration in the air itself at a point.
And to give you an answer, we're flying at several thousand feet above the surface in our outflow regime. And I apologize for my dogs that you hear in the background.
Not a problem. I'm quite used to it myself.
Okay.
Yeah, once you get up above a few thousand feet, where there's something called a boundary layer that is directly connected to the Earth's surface, but then there's a temperature inversion at a few thousand feet above the surface, and all the pollution stays in that first few thousand feet. So as long as you're above that inversion and looking down, you'll get everything. And so where Riley flies is, as long as it's more than a few thousand feet above the surface, isn't critical. But the techniques are quite complementary.
Yeah, and that's what's really impressive, is that we're getting roughly the same numbers from completely different approaches.
And I guess that was going to be my next question is, were you surprised that they were that complementary? I feel like I've seen some of these different presentations and they've talked about the different ways looking at emissions, and you kind of hear people say, well, this way is better, no, this way is better. But the fact that these came out pretty complementary, I find very helpful, and I'm just wondering if that sort of surprised you at all.
It surprised us after the fact. While we're analyzing the data, we didn't look at his results. We didn't want to be biased, so we just plotted along. But then looking at the final results, yes, we were surprised.
But well, and one of the official inventories instead of 25 had the number 7. So yeah, there's a lot of disagreement, but it says, well, maybe we got lucky, maybe we're both wrong the same way. But I think it's just, if you're really careful, the techniques are maturing.
Yep. What's also been very interesting is that maybe Dan Zimmerly in his next talk can comment on this, is that the ethane has gone down significantly. And he's got some thoughts about why.
Okay. Those were the only questions I had. Thank you, Mr. Chair. And thank you for the presentation.
Commissioner Bogue?
Thanks. Great presentation. So quick question about sort of total methane flux over a given year. So obviously, this is October. The previous study from Carbon Mapper indicated that when they did a summer flight, a much larger proportion of the methane emissions were determined to be from CAFOs versus when they flew in the fall. And so I'm just curious if what your thoughts are on this estimate of sort of 70 to 80% of methane emissions in the DJ being associated with oil and gas operations, how consistent that might be over a given year, or if you think there is a seasonality to it that's going to change, depending on the season.
There could very well be a seasonality. So next year, we are hoping to fly either in the spring or the summer well, we'll see about the availability of the aircraft next summer, but certainly in the spring, where we hope maybe to get some information about that very question. The other thing of note is our analysis of 70 to 80 some odd percent attributable to oil and gas was a very rudimentary procedure, and we're hoping to follow up with some more sophisticated analysis if the data is there from the proton transfer mass spectrometer. If that we can get, if we're lucky enough to have appropriate data, and we'll look at that very soon, we can do some more sophisticated analysis to buttress those results. So the answer to your question, we're hoping to do some more work and maybe to address the seasonality of it.
So if I may, very quickly, there are two kinds of major biogenic sources, and there are landfills and manure piles, and they respond, wetlands, they all respond to temperature. Higher temperatures, the bacteria grow faster, but cattle are mammals, and so enteric fermentation. I don't know if there's seasonality in the number of cattle in the feedlots. I don't think there's a huge change, but their response to temperature is much less. And maybe the demand for natural gas has a seasonality. I know use has a huge seasonality, and leakage from the natural gas delivery system appears to be greater in the winter than it is in the summer. But so perhaps as it gets cooler, there's more methane generated. I should know the answer to that, but I bet Zimmerly does.
Commissioner McGowan?
Thank you, Mr. Chair, and thank you for the very back in college presentation. I'm not sure I understood. I feel like I heard both things, which was the actual inventory shows numbers that are lower than modeling, or the modeling is actually underestimating actual numbers. So I feel like I heard you say both, and so I guess I'm trying to understand, when we look at the actual inventory and the numbers that you see, is that more or less than the modeling that's being used for regional air quality?
I don't know what the regional air quality model is using for methane, and methane by itself doesn't generate much ozone in Denver. What I'm saying is that the numbers that we get from direct measurements and the numbers that Riley showed you from his remote sensing are in agreement, and they're all about 3 times higher than is in the European global emissions inventory. So I suspect that the people who do photochemical smog modeling in Denver have much better numbers, but we ran our model, but they don't care about methane so much. Methane doesn't make Los Angeles type smog in Denver. The other things do. So the official global models are not capturing the amount of methane that Colorado releases. And I suspect that the Colorado Department of the Environment, that's not its proper name, I'm sorry, has better models.
That's helpful, thanks. I was getting confused about our regional model and ozone versus methane and what modeling you were talking about. So that really helped, thanks.
Okay, yep, sorry if we confused you.
Other commissioners with questions? I have to follow up just one more time on Commissioner Cross question to make sure that I understand. So on the conclusion end of things, we've got an overall emission of methane that is relatively flat, despite a factor of approximately 2 times increase in production between 2015 and 2021.
Right.
Two times, right? So 2-time increase.
Yes.
Yes.
But ethane, which I thought I heard you say that ethane is directly related to oil and gas activities,
Yes.
has actually decreased. So this flat methane, I guess I don't understand how that correlates between oil and gas. I guess I'm not putting those two things together.
So the reason, and Riley can comment on this better than we, is according to what Riley explains to us, not Riley, I'm sorry, Dan Zimmerly, is that there's been significant improvement in the device structures. And so in that there's been a reduction in the pressure of the gases coming up at the wellhead and then flowing into the reservoir tanks. And the tanks themselves selectively store the higher hydrocarbons, ethane, methane, propane, butane. And if the pressures are lower in the tanks, there's less flashing. And the lower the flashing, then the lower the emission, the relative emissions of ethane, which has been separated from the methane. So that will affect the ethane methane ratios, because things have been separated already before they go into the tanks. But
Yeah, let
Dan-
me add a little something that
Yes.
you can put the ethane out with the natural gas that you sell that goes into your furnace. It works even better than methane. On the other hand, there's a market for that ethane. So if your engineers can strip it out, they can sell it to people who make polyethylene out of it and make a lot more money than just adding a little oomph to your natural gas. So the engineers have done a good job. Apparently, they're stripping that ethane out and other higher hydrocarbons and selling them so they don't get into the atmosphere. That's our conclusion. But Dan Zimmerly is really the engineering expert.
Right. And the way Dan explained it to us is that perhaps there's 3 stages of pressure regulation that's been enacted since 2015 or so. And the newer wells have enacted this additional pressure regulation. So the newer wells have taken up a greater proportion of the total amount of active wells. And so this is our rudimentary understanding. But we're still looking into this.
Okay.
Great question, though.
Yes.
And so just so I understand timelines here, so I mean, you've done these flyovers, this research up to this point came up with the information that you provided today, which is spectacular. You're anticipating some additional flights to occur this next summer as well, and then you'll kind of compile this information, or will you just continue to do flights and continue to?
Well, we have additional flights to analyze from the fall studies. So we are looking at those now. So those will go into our overall conclusions. But yes, we hope to have additional flights coming up next spring or so.
Yeah, we were funded for this pilot study. We're hoping to get funding for additional flights in additional seasons and additional basins in Colorado.
Right.
Well, really appreciate you guys being here today, presenting the information. Certainly, I found it incredibly interesting and helpful. So thank you for your time.
Thank you.
Is everyone okay to keep rolling here? Does anyone need a break, or are we okay? Okay, we'll keep going. So next up, we have Daniel Zimmerly, the director of the Methane Emissions Program at Colorado State University. Welcome, Mr. Zimmerly. It's a pleasure having you here today.
Yes, excellent being here. What I'm going to do is CSU actually has 3 projects in this space. And sitting beside me, just strategically off camera here, is Stuart Riddick. So we're gonna. Can you see my screen first of all? Did that come up?
Yes, we can.
Okay, great. So we have 3 projects, and I'm gonna do the coordinated campaign. Kate Smith, and if Kate's actually on, if you could just let her in as well into the panel, that would be great. And then so I'm going to do the Colorado coordinated campaign, and then Kate Smith and Stuart are going to do the pipeline funding that you provided for us. And then the other project we're doing is abandoned wells. And so I'll just have Stuart chime in for a few minutes right before we start here. And he can just we just started this. I mean, it's like 4 weeks old. Yeah. And so I'll let him give you a quick update on kind of where we are with the abandoned wells stuff, and then we'll launch into C3. So
afternoon, everyone. So we've been tasked with measuring methane emissions from abandoned oil and gas wells in Colorado. And this came through Department of Natural Resources, who handed us a data set of abandoned oil and gas wells, or orphaned wells, that they're either plugged or are due to plug in the near future. And I've been going around visiting the wells and seeing, first of all, scoping out to get access, and secondly, to measure emissions if possible. Just to give background on abandoned oil and gas wells, the average emission in the US is around 8 grams per hour per well. So that gives you a baseline of what we're working on. So since since the end of August, I've been visited 300 abandoned or orphaned oil and gas wells. I've measured around 120. Half of those have been plugged and half of those have been unplugged. I haven't seen any plugged wells to date that are emitting, and part of the reason for that is that in Colorado, you plug with concrete, seal the top, and then overfill with about 6 feet of soil. What I have found is with the unplugged wells is that the average emission is over 1 kilogram an hour, and that's to do with the wells that are being abandoned in Colorado and how different they are from Appalachia, for example, where a lot of the previous work's been done. So that's a quick overview and some sort of early headlines from the project. Thank you very much.
Great,
So
thank
any
you.
questions on that one before we go on?
Commissioners, any questions on that? Commissioner McGowan?
Thank you, Mr. Chair. Not a question, but I think there's also going to be a report after they assess all the wells, and they're doing some this summer, and they're going to do some in the colder months so we can compare. And so I think the commissioners might have some better data and be able to ask some questions when we have some more information.
Great, thank you, Tim.
Okay, great. Thank you. Okay, project number 2, the Colorado Coordinated Campaign. So just to give you, to put this in context with what you've seen so far, is there's the coordinated part of this is that there's top down and bottom up stuff going on. So there's aircraft making measurements at sort of a basin scale. We're using some of that data. And then you can kind of think of us as sort of being the blue collar group that's going around to individual sites and making measurements of those sites. In general, it takes a lot longer to complete on our side than it does on the measurement side, because we are usually waiting for several months for all of the data to come in that we need for the analysis. And in fact, one of our principal data sources for this is the 2021 greenhouse gas reporting to CDPHE, which first went in at the end of June. So it was due at the end of June. So we're literally mining data from last year that's being presented or being submitted this year. So we have 2 objectives. One of those is to build a better bottoms up model. So you've heard about those a couple times already in the discussion. And our job is to, kind of come up with a better way of modeling. That was from an inventory perspective. And then the other thing we're doing is we're working with CDPHE and others on how they can use those models for their regulatory program. The actual way we're doing this has kind of changed direction over the course of the project, because originally it was more of just a study and leave. And because CDPHE is moving forward with some different ways of, or let's say, providing options for people on how to calculate their emissions, we're much more involved in that now. And so we have had a series of intensive meetings with operators in the basin to get their input on how we're going to model their sites. And then we're also using as much data as we can harvest from all over the place to build those models, and then keeping CDPHE up to date on the same side. So you can kind of think of it as being sort of in between a conversation between the operators and the operators with us, and then between us and CDPHE. Okay, the coordinated campaign was coordinated as much as we could with Carbon Mapper and the University of Arizona. And then down on the ground, we did a series of different kinds of measurements to assess the emissions from primarily well pads, but we also did some compressor stations as well in July. And then we've been working a little bit more distantly with the methane-ethane flights that Ellen Freed and Russ Dickerson are doing, and that you just heard about, right? And so at the, you can kind of think about the Riley's flights, the carbon mapper flights, give us kind of point sources, and we're sort of doing point sources. So there's kind of a comparison, apples to apples type of thing there. Whereas we can't really compare to the University of Colorado work until we've got a model of the whole basin running. Okay. Okay, so here's the coverage area. The gray in the background is the actual flight paths of the carbon mapper aircraft. And then it's overlaid with a bunch of different infrastructure. You can see the plume, kind of scaled plumes locations. There's the stars. And then there's the production from the pads, production pads, which are the round circles. And one of the first things that'll strike you about that is that the plumes are not on the highest producing facilities. Okay, which is sort of an interesting bit. We have a little bit more work to do on those, but it's not like you see all the plumes kind of clustered around the top of all of the higher producing facilities. But this also gives you a pretty clear picture of where the production happened. So Shane Murphy from the University of Wyoming is working with the group, working with my team, and they're rolling up all of the measurements that were taken by the ground teams in the project. So we did that in a couple of ways. One of them is we do what's called a drive around method, where we come to a site like this, we drive a loop inside the site, and what we're looking for is elevations in the methane concentration above background of a 1 ppm or more. If we see that, then we go ahead and measure the facility. If we don't see those, we say that facility is tight and we move on. And we've used that approach because it allows us to get to a lot more facilities per unit time than we've done in other campaigns. The second technique we used is tracer release that we use for large facilities. Every time we're going to do a large facility, and then we use tracer release on some well pads. The problem we had was that when we tried to do tracer release in July, the wind was crap. And in fact, I don't know that Riley mentioned this, but there were a couple of days they couldn't fly for the same reason. We basically, none of these methods work if you don't have some predictable wind transport. And we certainly did not have that. So despite trying for literally for more than a week in July, I think we only came up with 1 or 2 measurements with tracer. And then the last method that we use is called OTM 33A, which doesn't use a tracer method. I don't think you really need to know about all those methods, but if you want to know more, just interrupt me and we can talk about how those work. Okay. And the last thing is we collected VOC canisters when we were doing the measurements. So we had a VOC measure. We could send those away to a GC and get those speciated so we could see some VOC information. And that was done by Jeff Collette's team here at CSU. Okay, here's a kind of the campaign results. There's about 2,500 well pads, compressor stations, and the like in the DJ basin. We visited about 335, which is a fairly high percentage for a field campaign, actually, to get to that many. Of those, we had elevated emissions that were warranted coverage on about 45 of those sites. So we made measurements kind of at 45. We had uncooperative winds in July, which knocked out most of the midstream sites. So as moving forward, I don't think we would try to measure midstream the way we were trying to measure it, because we really have to, we can't coordinate with the aircraft when we're doing it, because we have to do it when the wind is right. It doesn't, otherwise it just flat out doesn't work. And then the other part that we picked up was VOC numbers. And so we have about 42 pairs of samples on that. So all of this data is in progress right now, and it's got a specific purpose. What we're going to do is we're going to take all of the data you see here is primarily intended to tune the bottoms up model. So what we're looking to do is to take the measurements we have of individual facilities and the cause and effect data that was collected by the teams when they were on the sites in order to improve the bottoms up models for the basin. The last thing that we've been doing, and let's see if I don't know if I'm going to be able to get this to run, but the last thing we've been doing is one of the key questions that we've had for many of these field campaigns was a question about whether the aircraft, when it's flying over the basin, is seeing maintenance events or whether they are seeing unknown emitters. So basically something that's a fugitive that wasn't known. And so what you see with these flashing green spots on the screen is those are locations at which maintenance events are occurring. And occasionally, if it's coming through on the broadcast, you can actually see the aircraft going overhead. And then every once in a while, one of those green dots turns into a persistent red dot. And that's where the aircraft had a plume that landed on top of a known event. And so this is a partial set of data where we actually have to regenerate the animations here because we got the data from the last company that's participating just recently here, and we haven't regenerated it. But first of all, it gives you kind of an idea of how many events are happening for maintenance events. Most of those are not, well, to say they come in a whole range of sizes. So some of them may be very detectable and some of them may not be detectable at all. Okay, but in addition to that, you can see even though the aircraft is flying overhead kind of on a routine basis, the number of times that they fly over an event and they actually pick it up as a plume is quite small. I expect that paper we'll probably have that out by early November, and we'll have kind of final results on that data. Okay, so the last bit we're doing is kind of this cooperative effort where we're sitting between the operators and their understanding of the site emissions, the emissions data that we've collected, and then the usage of that data to improve models. So we have two problems we need to solve on this. The first one is we need to model the facilities in a fairly accurate way. So we've created about 15 prototypical facility models in conjunction with production operators in the basin. So we've literally sat down with them in rooms and we've sketched out on the whiteboard what the piping looks like at their facilities, what the pressures and the temperatures and the control systems look like, to try to understand kind of how their systems work and where the emitters would be. And so that's kind of in prototype. So those prototypical phases have been prototyped, and we're right about at the point where we're going to start going back to the companies and saying, now, based upon what you told us, this is what we modeled, and this is the kinds of emissions we would expect. That part's kind of moving along fine. The other one is we need to get a complete site list, and we're finding that's been a very interesting challenge. Okay, so we've fallen back now to the point where we're primarily bringing in the site list from the latest reported data to CDPHE's greenhouse gas reporting program, and we still have some issues with that they're trying to work out. So once we get both of those pieces in place, we can run the models, we can summarize them in various ways, we can match each individual site in the basin to a prototype and create a geographically distributed site emissions measurement. Right? The purpose of doing all of that is to make some comparisons. So we can use the prototypical models that we're producing to give us time series emissions. And so that's useful for evaluating things like driving surveys or flying surveys. So if you fly over a site or you drive by a site and you get a certain emissions measurement on that snapshot, you don't know whether that's something that's within the range of what that site should be producing based upon what's being reported. So that's what we use the full time series for in the site probability distributions. And so that would be comparable to, for example, Dan Bond's got some ability to move a van around and sample various sites. He would use that kind of information. And then we can also look at annualized or average emissions, which is where the reporting improvements would come from. It's also the type of data that we're going to compare to Ellen and Russ's flight data. So just so you can see what one of the facility models look like, this is a typically what they look like and sort of what the content is. We're getting well production off of COGCC's databases. We've got pressures and temperatures and number of separation stages for about 15 flavors of well pads. We have some basic models in place already for compressor stations, and then rolled together, we're going to get an estimate of the emissions that includes failure modes that happen on those facilities. And then we're going to compare those with what the companies are seeing in their sort of day-to-day operations, to make sure that we're modeling those as best possible. I'm not going to go through this last slide on here. You got it in your deck. And this is sort of talks about some of the issues that we're working on in terms of improving those models. And so I think probably at this point, it's maybe best to just step back and ask questions, and we can jump around in the slide deck or whatever. And then we'll pass it on to Kate for the pipeline stuff. So.
Great, thank you. Commissioners, are there questions on this piece? I don't see any questions at this point. Perhaps we'll go on with the next one and then come back to you if there's additional questions.
That sounds good. So Kate, I'll quit sharing and I'll get out of the way. And then let's see, where's the unshare button? I've lost it. Zoom. Okay, great. Okay, good. So and I'll turn the screen here so that Stuart's in view and I'm out of here.
Can you all see my slides, or are you seeing the right view of them?
We're not. I see your note.
Yeah, let me get the other view here. This way. All right, you seen the right view?
Yes, we are.
Okay, great. All right, so as Dan mentioned, my name is Kate Smits. I'm a professor at Southern Methodist University, and I've been working with Dan and Stuart on this project for the last couple years here. And I'm going to be presenting in the first part of this talk, and then Stuart's going to chime in towards the end there. Our project is on upstream pipeline safety, integrity, and detection. So the project, as y'all know, it was funded by the Mark Martinez and Joey Irwin Memorial Public Trust Fund that's administered through the COGCC. And our project focuses on pipeline leaks from upstream operations, with the goal of assessing and then improving earlier and more effective leak detection. So the main objective of our work is to improve the performance of both existing and emerging leak detection methods. So that's what we're really focusing on. And you'll see how we've linked some of our project work with a project we have that's funded through PHMSA, so that we can understand the below ground migration, the surface presentation of pipeline leaks, and then what happens to them after they get in the atmosphere, and then how we can work all of this knowledge into operator practice and improve our ability to detect leaks and then, of course, mitigate their consequence. So this is our joint study team from Colorado State University and SMU. I'm the talking head today, but this is a joint effort with lots of research scientists and graduate students, so PhD and master's level students, and we even have undergraduate students that are working with us in our research group. So the Upside project, as we call it, focuses on pipeline leaks from upstream operations, with, like I mentioned, the main objective of improving performance of existing and emerging leak detection methods. So we focus on a range of leak sizes and different gas compositions. So Stuart's going to talk in a little bit about wet gas versus dry gas and how that can be factored into how well we're able to detect leaks. We're looking at the above ground leak detection technologies with this project, but how that links with below surface and atmospheric understanding. So our project was funded almost, within a month of a PHMSA project that has a different focus, but a really nice synergy with our Upside project. So we have a currently funded PHMSA project that looks at mid to large leak scenarios. So we're talking about 20 plus standard cubic feet per hour. And really, we've been focusing on really big ones like 100 plus standard cubic feet per hour. And what we've been doing with this project is very high resolution field testing that I'll explain in a minute with our approach, so that we can characterize the gas migration behavior within the subsurface under a large range of environmental conditions, and then link that understanding with first responder and leak detection protocols. And we just got a follow-on project sponsored by PHMSA to this project that actually looks at more diverse operating areas and environments and environmental conditions. So, when you see some of our results, they're for our conditions that are tested, and we're really excited about our follow-on work that looks at more diverse operating areas and conditions. So with our approach that we use with our research to address our research objectives is to link experimentation with science ideas and mathematical modeling, and always operator practice. So we perform controlled experiments for this work at the field scale. And then we use those experimental results to understand what's happening in the environment, but then also link it with numerical models so that we can develop solutions with our industry partners. And then we also, of course, take this to the field and perform experiments with operators. The pictures you're seeing in the middle are of METEC. METEC is the Methane Emission Technology and Evaluation Center that's at Colorado State University. And the pipeline test beds are what we're using for this work, and I'll talk about them in a minute. We have been running our experiments in collaboration with different fire authorities. So we had Poudre Fire Authority, which is from Colorado, Fort Collins, out doing a lot of the experiments with us, and that's the picture down in the right there. So METEC is a 7-acre facility. I don't know if any of you have had the opportunity to venture up to Fort Collins yet to visit it, but you're always welcome to come on up there. And even if you just want to drop by sometime, please let Dan or Stuart or I know, and we're happy to give you a quick tour. It's not like it needs to take all day to go look at it. And what we do at this facility is we simulate natural gas emissions from production, gathering, and a bit of the distribution systems. And so that includes these underground locations. So the site includes, I think it's 200 or so above ground emission points. And then we have the part that we're interested in for this work is 8 simulated pipeline right-of-ways. So that's the yellow that you're seeing in the picture. And in those right-of-ways, we have 25 controlled emission points. And then we also have constructed 7 additional pipeline test beds that simulate both rural and urban environments. And we're able to simulate leaks from 0 to about 100. We've tried a little bit more, standard liters per minute leaks, and control them with different types of gas, with dry gas and wet gas. But what really makes our test bed unique is that it's equipped with, I call it an optimized matrix of sensor systems, so that we can monitor all the time the methane concentration, the soil environment, and all of the atmospheric parameters. And when we know all of that information holistically, we're able to, number one, ask interesting research questions, but then 2, try to advance the safety of our natural gas infrastructure. So with this project, with our Upside project, along with our PHMSA sponsored project, over the last year and a half, we've conducted over 100 pipeline experiments. So this is where our amazing graduate students come in to the mix. And what we've been doing is very systematically going through different factors or parameters as we have expressed here, whether it be leak rate, natural gas composition, moisture conditions, because we know soil moisture has a big effect on where the gas goes. Looking at different environmental factors such as big rainfall events, really dry, arid Colorado days. But then when we get these big snow and ice dumps, what does that do to the gas migration conditions for safety purposes? We're able at our site to modify the surface conditions because we have pavements that we're able to pick up and move. So as you can see in the bottom right there, we can simulate different scenarios, whether it be a home with a patio or a walkway or driveway, etc. And then the last thing, we've varied the subsurface conditions. So whether we have a rural environment or an urban environment where we have competing utilities, we're interested in looking at that as well. So instead of trying to boil the ocean for you today, we're going to just focus on 3 highlights of our research findings so that you have something that you can sink your teeth into and walk away with. The first one, I'm going to talk about the first 2, and then Stuart's going to jump in and talk about the last one. So the first one is that we found through our work that the gas moves further and faster than we had previously thought. I have right there, not for the obvious reasons that folks often say. And that gas continues to move in the subsurface even when the leak is fixed. And so these findings are, of course, important to leak response. Then I'm going to talk about how we've figured out ways we can estimate the probability of leak detection success based on environmental conditions and operator practice. So looking at, if the weather conditions are a certain combination today, what is our probability of detection success compared to a perfect day? And as we change those, how does that affect our probability of leak detection success? And then Stuart's going to talk about how the gas type, so if we have a wet gas versus a dry gas, how this significantly affects the subsurface gas movement. And then therefore, and then in addition, you'll see the plume development, and that of course affects our leak detection best practices. So the first one with the gas moving further and farther, I'm just going to give you one example with the snow cover. So this is something that we were able to do this past winter because we had some really nice snow dumps back in, I think it was February timeframe. And so when a leak location is covered in snow, what we found was that the leak migration distance increased, but it increased a lot more than we thought it would. So in this case, we saw for the exact same leak scenario, so this is just giving you one example of hundreds of, we had a leak at 11 standard liters per minute, and that leak under the same snow frozen topsoil condition moved 5 times farther than the dry grass covered, arid summer condition that we had in similar timeframes. So in addition to this, the concentrations exceeded the lower explosive limit further and faster than the dry grass conditions. And in this case, the lower explosive limit for the snow and frozen topsoil was reached about 10.5 feet from the leak location within 6 hours of the leak initiating. So the snow was, of course, serving as this cover that the gas was not able to release, and so it then increased the lateral transport of it, but then also the lateral speed of it. What is of great interest to, I think, safety concerns is that even when the leak was stopped, so if you can assume, we just have to turn the leak off, but in an operator practice, that would be equivalent to fixing the leak. The gas continues to spread laterally underground away from the leak point at concentrations that exceed LEL. And so going back to I liked Karen's comment earlier about a science class here. So if we just have a little bit of science class, that's because of the property of diffusion. So the gas wanting to move from an area of higher concentration to an area of lower concentration. So just because you fix the leak doesn't mean all of the gas goes away underneath the ground. The gas is still there at levels exceeding LEL and can continue to move outwards, especially, and then that's elevated when we have a snow or frozen topsoil condition. And this, of course, has a lot of implications for leak repair. So I think the main one is that additional caution needs to be taken when responding to leaks during winter conditions. I don't have time to talk about this today, but we saw the same conditions, the same spreading when we had very heavy rainfall conditions. So to simulate that, that's where the Poudre Fire Authority came in and helped us with their humongo trucks to have some nice heavy rainfall events. I think that this is also important to leak classification, because a lot of times a leak classification is determined based on just, nice day conditions. But if we know that the gas has the potential to spread farther, if there is potential for snow or frozen topsoil condition, and in this case, 5 times farther, I think that this is a very important finding to leak classification. So with all of our work at METEC, one thing that we're very in tune with is our industry advisors. And when we have findings like this, I have 2 citations down below. We release these as research alerts and get them out to industry as opposed to waiting for the fancy research publication to come out. So that's our way of trying to continuously connect our findings with our industry advisors, as well as our industry advisory boards that we have as part of this project. Just very quickly on this one, this is showing that we also ran these experiments under a range of surface conditions, whether it be driveways, patios, asphalt, grass and snow, etc., and had similar results. All right, so I'm going to move on to the next one, which is the probability of leak detection success. And with this, what our goal was to investigate detection probability of mobile survey solutions. And we specifically focused on walking and driving survey for natural gas pipeline leaks. So the driving survey, as we know, has been increasingly used as an option to detect and assess natural gas pipeline leaks. And I think one of the primary advantages of a driving survey is that you can get to more areas more rapidly, which is great than walking. However, there's really no robust evidence that proves that the driving survey is as effective as detecting a subsurface leak using a traditional walking survey. So there's this gap that remains in our understanding of the effectiveness of a driving survey in efforts to detect a subsurface leak. So with our study, what we were interested in is investigating how the leak rate, the survey distance and speed, and the atmospheric conditions affect the detection probability in controlled underground releases with a range of leak rates. So I think we went from like a half to about 10 standard liters per minute of leaks. And we walked across these exact same leaks for weeks. This is one of our graduate students, Shan Rue, walking 3,000 times across leak scenarios in order to get enough evidence for our statistical analysis to look at the probability of detection. So we were trying to answer the question of what conditions have the best probability of detection, but even more so, how does the changing condition affect the probability of detect? Because we can all probably say, a nice day with very little wind will probably be your best bet for probability of detection when we're talking about a walking survey. But what is really the effect of changing the conditions on the probability of detection? So what our results show is that the detection probability is highly influenced by the survey speed. So how fast the survey is going, whether we're walking or driving at a certain speed. It's highly dependent on what we call the atmospheric stability. So atmospheric stability is more than just your wind speed. It's a combination of your wind speed, your pressure, So your barometric pressure, your temperature that you have in the atmosphere, et cetera. And then also, if we want to focus on one atmospheric parameter, it is affected by wind speed. So let's first talk about the survey speed only. So how fast someone's walking or how fast someone's driving. And I'll give you just one example. So if we go from a low survey speed, so somebody that's walking about 2 to 10 miles per hour, we generally have what we found about an 85% probability of detection when we have a very stable atmosphere. And so what that means, if we're just talking about wind speed, to try to keep it simple, is that when we have a wind speed less than about 5 meters per hour, the probability of detection then decreases to about 25% under the same conditions when we have when we're driving between 25 and 35 miles per hour. So what that's saying is if you're going across the same leap, your probability of detect is 85% when you're going at a slow speed of somebody walking. But if you take that exact same instrument, you stick it in a vehicle and you're driving between 25 and 35 miles an hour, your probability to detect, if you're not changing anything else, is going to be 25%. So your probability to detect with a driving survey is going to decrease quite a bit. Now let's look at wind conditions, because the wind conditions is a big factor. So the detection probability, it decreases to 50% when the wind increases from 2 to, I think we did 12 or 13 miles per hour. So this is still really low wind speeds. When I go out and talk to operators, they don't stop doing detection until we're at about 20 miles per hour with wind speed. So what we saw is just within that range of 2 to 13 miles per hour, the detection probability reduces 50%. And so this, of course, has a lot of implications for leak detection solutions because, like I mentioned, the driving surveys have been increasing, and our results really show that with an increase in the survey speed, the probability of detection rapidly decreases. And that's okay, assuming that, we work that into practice. So, what we really showed in this paper was that driving survey can only be done at a low survey speed and a low wind speed if you want to achieve equivalent detection probability to a walking survey. So it's all, what are you trying to do? And if you're really trying to find leaks and to detect them so that we can mitigate them, then we have to take all of these things into consideration. Okay, I'm going to hand it over to Stuart, who's going to talk about linking the subsurface gas movement to the atmosphere.
Thanks, Kate. Yeah, as Kate said, what we're talking about is linking subsurface to the atmosphere, and that has implications to both improving leak detection solutions and improving the quantification of subsurface leaks from above ground measurements. So this came about, and it's currently in analysis, looking at wet gas. And so wet gas is gas with heavier hydrocarbons than dry gas, which you might have methane of in the 90%. And very wet gas, you might have methane percentages in 60%, with other heavy hydrocarbons making up the rest of the gas. Thanks, Kate. So the findings from the Upside project, and this is Mercy, that one of our grad students that did a lot of these measurements. The plume width downwind of a subsurface leak was seen to change with gas composition. You see the graph there very simply is, it's all 10 SLPM of gas. The blue bars represent pure methane, the orange methane and ethane, gray methane, ethane and propane, and yellow with butane mixed in as well. And these were measured at 7 meters downwind of the subsurface leak and at different heights. So the height of AGL, that's above ground level, 0.5, 2, 5, and 7. And you can see here the plume width for the methane was relatively consistent across the different heights. But as the gas becomes heavier, the width of the plume becomes smaller. So that means, therefore, it's a bit more difficult to detect. And the interesting point here is that if you have a measurement system at 5 and 7 meters above ground, you won't detect the wetter gas. So this obviously has implications for leak detection solutions such as drones, which are flying at between 5 and 7 meters and even higher, that if they're surveying in wet gas regions, that they won't actually detect the plume at all. Thanks, Kate. This then goes on to the R-Plume project, where, as Kate was saying before, is observing gas speed and distance from the subsurface leak. And the leaks were made of different gas compositions as before, and the methane was observed to travel farther horizontally in the soil as the gas gets wetter. So there's some ideas here that as the gas gets wetter, the methane travels further horizontally and doesn't enter the atmosphere at the same point. And as I say, this is some work that's under analysis at the minute, and we're trying to understand the mechanism by which this is happening. Now, the sort of overall idea of this is to produce a synthesis paper between the Upside and the R-Plume project. And if we click the next screen, thanks, Kate. We can potentially use something like the escape model, which our group published last year, which was looking at the flux of the atmosphere when you take into account the surface, the subsurface, and the atmospheric resistancy. So it's very simple Ohm's law equivalent. And so you've got flux of the atmosphere as a function of the resistance and the difference between the concentrations. Now, what we're hoping to do is use the R-Plume data to tune the model and generate an algorithm for above surface plume size and width. And then we will hopefully validate the algorithm with the Upside data. So it's using the R-Plume data to generate the model, then validate it with the Upside data, and use this validated algorithm to optimize leak detection approaches. So looking at, if you take the DJ Basin, if you go from north to south, as the gas gets wetter, you may have to change your leak detection solutions if you're traveling in different regions of the basin. Now, this obviously has the added advantage that it's bidirectional, and we can estimate leak rates from a detection and gas composition. If we can measure the size, the width of the plume, we can then infer the size of the leak below the surface using this approach. And this is ongoing work, and hopefully we'll get this produced in the next year or so. Thank you very much, Kate.
Thanks, Stuart. And yeah, this just kind of shows what we've done so far and where we're going with the project. We're working on some numerical simulations like Stuart was talking about, and then linking the above and below ground behavior and linking it with our first responders. I put this little chart in here, this expected outcome, because when we sit there talking with operators and show them this stuff, it makes their eyes roll in the back of their head. But what we're trying to do is link it in such a way that we can be able to say, during a leak, here is the best conditions to do leak detection, and this is how that behavior changes over time, and you can work that into your operations. So that's all we have. We're happy to answer any questions that you have, and here's our contact information should you want to reach out at a later time. And like I mentioned earlier, you're always welcome up to Fort Collins to take a look at our METEC site, or if you're ever in the DFW area, you're also welcome down at SMU. So we've also been working a little bit with the Texas Railroad Commission on this project. They sit on our advisory board, so to get a different perspective as well.
Great. Thank you very much for the presentation and the information that was provided. And I would love to take you up on coming to see the METEC facilities. So perhaps we can make that happen over the next.
Sure. I mean, it's just a matter of arranging a time, and you all can come up either as a group or individually, however it works out.
Great. Commissioners, are there questions? Commissioner Krause?
Thank you, Mr. Chair. And I'll say I don't necessarily have a question, but I just want to say this is very helpful. I particularly like the idea of being able to say, hey, based on where you're operating and the type of operations you're doing, this is going to be the best way to find a leak. I find that incredibly fascinating and extremely helpful. So thank you. These presentations overall have been very, very helpful, and I really appreciate it.
So I've got a couple questions. So with this particular research, is it I mean, are the end users for this really the first responders as far as how to deal with it when they're trying to address a leak? Or can it also be used for developing policies or protocols within an operation to kind of continuously monitor for aches? I mean, what's the primary end user for this, I guess, this data?
So,
Dan, take
yeah,
that one.
sure. Yeah, I'll chime in here. So I think that there's probably several different messages delivered, particularly with the pipeline work. The first one is that there's a tendency to assume that the leak detection methods you can use for above ground leaks are going to just work the same way for below ground leaks. And Kate's team and my team have been working on this now since 2014 or something. It ain't true, okay? And so part of it is sort of changing people's mindset about how stuff will work. And that hits two areas. The first one is picking tools to do the pipeline leak surveys. And the second one is doing the surveys correctly, okay? Now the PHMSA project is a bit different focus. The person who's most likely to get injured or killed responding to a gas leak event is the first responder. The person who's there trying to figure out what's going on is the person at biggest risk, actually more risk, as it turns out. I think Stuart did the data on this, more risk than the people who evacuated the house, right? And so that one is targeted at first responders. But again, while you're doing all that work, you just find out that things don't behave the way everybody's been assuming they work. And so that produces a whole series of scientific findings and then also policy. It's directly policy impacted because it's going to eventually, at some point, impact how people look for leaks.
And I think one of the things that we often hear from operators as they're proposing new oil and gas operations is remote detection technologies or remote sensors, or being able to regulate or tell if there's leaks based on pressures of systems and things like that. Is that something that you kind of evaluate as well in your data sets and as a potentially effective or not effective technique?
We have not looked at the ones that you mentioned yet. We've reviewed them. Dan and I put a few reports together in the past that we can share with you that look holistically across different technologies and cons for those specific to pipelines. With this work, we were specifically looking at above ground technologies, and just to kind of elaborate, one of the things that Dan was saying, and then that you brought up as well, John, is that there is no equivalency that has been put in place across these different approaches. So we have Dan's comment that shows that the above ground technologies may not transfer directly to underground scenarios. And that's because of, this diffuse presentation of the leak, the below ground transport properties, the extended geometry that we have of the pipeline, and then the differences in the operator practices. But then linking that with, we've never done equivalency studies. So there is a big space and a big gap in our understanding of all of these different options. And are they as good as something else? We don't know the answer to that. In fact, I think our paper on the probability of detection for the walking and the driving survey was really the first one to do that for pipeline scenarios. Right. And to look at that systematically over changing conditions and changing operator procedures. So there is a dire need for that in order to be able to say, is this as good as that? So, everyone's trying to sell everybody something, but what is the equivalency of it to something else? And there's a big unknown.
Got it. Thank you. I think my last question's to Mr. Zimmerly, based on your previous presentation, and I'm trying to tie it into some of the previous presentations we had before yours, as far as how we kind of tie all this data together, this emissions data, and we're hearing that based on some of the information from the flights and the two different types of flights, that we've got kind of flat methane emissions, but methane emissions still contribute approximately 70%, 75% of overall methane emissions, in the DJ basin. But we've got significantly dropping ethane amounts between 2012, 2015, and 2021, which I'm trying to understand. My understanding is that's directly related to oil and gas activity. So I guess I'm trying to still correlate how we have flat 75% overall oil and gas emissions based on, of the overall methane emissions, if we've got this like precipitously dropping ethane emissions. I'm not a scientist. I can't get my head around that one.
well, so I think the bottom line is that we have hypotheses, but no proof or no results yet on that. So, but I can tell you a couple of things that are moving in different directions, and so that movement, one could hypothesize that those movements might have an impact on that ratio, right, of methane and ethane emissions. So, and Alan, I think, teased some of those out. So if you think about the way well pads were built in the, let's say, 2012, 2014 range, which was what was sampled by Patron et al., and probably for the most part by Peischel as well, there is typically two stages of separation, followed by an atmospheric tank, and then a certain set of other stuff happens for controls on top of those tanks. Okay. Nowadays, the production is primarily shifted. I think I ran some numbers the other day, and something like 85–90% of the production is well pads less than 10 years old, or wells less than 10 years old. And a lot of the more recent ones have more recent designs of those sites now have 3 stages of separation. And so prior to the atmospheric tank, the pressures are now down into the single-digit PSI gauge before it goes into the tank, which means that you're flashing off a lot more of the gas products. So things that are gaseous at ambient temperatures, right? So that would include ethane and propane. It may, but it starts to taper off with butane. So you'd anticipate that the more of the ethane is being pulled off before those emissions go into the tank. Okay. So in theory, that would say, yeah, you would expect some ethane decrease. So that's one variable. Is that big enough to explain it? I don't know. That's a hypothesis. Now, the other thing that's happened is we've had production increase by a factor of 2 in gas production. And I don't know what the gas oil ratio has changed. I haven't looked at that. So when the gas production goes up, you have to transport that gas. That requires more gathering infrastructure. The gathering system is driven primarily by engine-driven compressors. So these are large engines, and they slip some fraction of their fuel. But because we're in Colorado and we've got selective catalytic reduction on the engines, Possibly they're moving out more methane in that exhaust than they are ethane, okay? And so that would mean you got one variable pushing methane up, which is sort of scales, more or less, or in some fraction with the amount of gas you're transporting. And then you've got another thing that's potentially pushing ethane down because of the difference in processing. Okay, but let's be perfectly clear. This is all hypothesis, okay? The nice thing is that we're kind of at the point now with the modeling where we can start to actually run some more detailed models on the ground up, where we can speciate methane and ethane. We can look at different site types. And so I'd say over the next couple of months, some of my team and students are going to work with Ellen, and we're going to see if our bottoms up models kind of predict that type of a change in ethane. But I want to be really clear that that's completely hypothetical. We have not shown that that's true. Okay.
Sure. No, I appreciate that. And then as you're looking at different point sources, or as you're continuing your research, will you break that production down into like pre-production construction activities versus regular production activities versus maintenance type of activities? I mean, will you get that granular? Or?
Yeah, so the answer is yes, but not necessarily from this project. Okay. Okay, so first of all, when we designed this project to get their site counts up, we avoided pre-production.
Okay.
Okay, because it's a much more difficult problem. And also, I know that Jeff Collett's been looking at it. So he's working on that as a separate effort. And then in combination with Jeff's team and my team, we have a separate project looking at pre-production emissions I think you've probably already heard about, which is funded by the Health Effects Institute.
Yep.
Okay, and that's going to particularly look at pre-production emissions, and it's funding the same model that we're developing here to include the causal effects of those emissions into this model. Okay. So it's kind of think about it as like two airplanes flying in formation, or two parts of an airplane flying in formation. We haven't brought those quite together yet, but it's the same team working on the same stuff. Right.
Great. Yeah, great to hear that all of this stuff seems to be kind of dovetailing together as well. So really appreciate it.
Or you could say that we're sort of like jugglers that have a lot of balls in the air, right? And at some point we have to catch all the balls at once. Right. It just seems like we add balls in so far. So we're getting very adept at juggling them, but the idea is that they'll merge together. Yes.
Commissioners, any other questions?
Chair, I just have a quick one.
Sure.
Thanks. So I applaud you for doing those research alerts. As a former academic, I know how slow the process can be, and when you're working on something with important implications, it's exciting to get it out. So I am curious though, do you ever hear back from industry or first responder practitioners about applications related to any of your research?
Yeah, so we have industry on our advisory board.
Right. Okay.
So those we hear back from really quickly. So from the broader industry, I'm not sure that we've seen much come back. It goes into PHMSA and eventually pops out the other side. So. Sorry, Kate, I think I talked over you.
No, that you're fine, Dan. Yeah, I was going to mention our advisory board, and they've been very helpful and we've even sent them to them before we've sent them out more broadly, and to try to get some of their inputs, and they've been very helpful in that, and yeah, and always responsive, and we have a good relationship with our advisory board. But I agree with Dan. I don't know how it hits a broader community versus going to PHMSA, or we send them over to you all too through our project managers. So.
Well, really appreciate you all being here and sharing all this information with us today. I'll be spending the next couple of days trying to absorb all the information and get my head around it, and continuing certainly interested in continuing to hear about these as the projects continue to evolve. So thank you very much for presenting to us today.
I think the first part of next calendar year, we should have most of the C3 stuff kind of pulled together. So maybe a February or March update on that would, at that point, should be fairly well synthesized. And the pipeline projects are largely done at that point. And so the results, papers are kind of going out left and right at this point.
That'd be great. If we get an update February, March, something like that, whatever seems like an appropriate time, I'd appreciate that.
Okay,
All right. Well, thank you.
Great, thank you for your time, for the opportunity.
thank you.
Commissioners, that is the extent of our agenda today. I think all we need now is a motion to adjourn.
So moved.
Second.
All those in favor signify by saying aye.
Aye.
Any opposed? Have a good weekend. Thanks.
Thanks so much.
Thanks, and thanks again to our presenters.